Have you ever just looked at a mountain range, with those huge flowing curves and thought to yourself, how on earth can solid rock bend like that? Well, in this explainer, we're going to dig into that exact geological mystery. It's one of those things that seems to just defy all common sense.
I mean, it sounds totally impossible, right? We all know if you take a hammer to a rock, it shatters into a million pieces. It doesn't fold. And yet, when we look out at the world, we see entire mountain ranges that look like gigantic carpets that have been pushed together and just crumpled. So what's really going on here?
To get to the bottom of this, we've got to start thinking like a geologist. That means we need to understand the absolutely immense forces at play deep inside the Earth, and more importantly, how rocks actually behave when they're under that kind of pressure.
Okay, I love this analogy. Basically, any force you apply to something is what we call stress. And the change in shape that happens because of that force, that's called strain. The key thing to remember is that rocks, just like anything else, are gonna deform when they're put under incredible geological stress. The real question is, do they break or do they bend?
And it turns out, the answer completely depends on where that rock is. See, near the surface, where it's relatively cold and not under a lot of pressure, rocks are brittle, they break. But if you take that very same rock and bury it miles deep in the Earth's crust, everything changes. The intense heat and the crushing pressure from all sides allow it to behave like a ductile material. Think of something like warm toffee, or maybe even silly putty. It can bend, it can flow, all without breaking. And that right there, that's the absolute key to this whole puzzle. So, okay, we've established that rocks can bend. Now, let's go ahead and put one of these incredible structures under the microscope. Let's talk about the basic anatomy of a geological fold. To put it simply, a fold is just a permanent bend in what used to be perfectly flat, horizontal layers of rock. And when I say permanent, I mean it. Once a rock layer gets folded, it's not just going to spring back into place. That new shape is locked in for good.
Now, every fold has a few essential parts. The first one you need to know is the hinge. You can think of the hinge as the tightest part of the curve. The very top of the crest, or the bottom of the trough, where that bending is the most extreme. And then, stretching away from that hinge on either side, you have what are called the limbs. These are the flatter, less curved sides of the fold. So you've got that tight hinge right in the middle and then the two limbs sloping away from it. Simple as that.
Now, when it comes to folds, there are two main types you'll see everywhere. First up is the anticline. The easiest way to remember this one is that it looks kind of like a capital A. It's an upward arching fold, creating a shape like a dome or an arch in the rock. And the opposite of an anticline is, you guessed it, a syncline. This is a downward arching fold. It forms more of a trough or U-shape in the rock layers. And what's cool is you'll almost always find them together, one after the other, like a series of giant geological waves frozen in time.
All right, so now we know what to call these shapes, anticlines and synclines. But this just brings us to the biggest question of all. What kind of unbelievable force is powerful enough to bend not just one little rock, but an entire mountain range?
I mean, seriously, just think about the scale we're talking about here. It's almost impossible to wrap your head around. This isn't some small, localized pressure. This is a force capable of crumpling the entire crust of the Earth. And the answer, of course, lies in plate tectonics. The Earth's crust is broken up into these massive plates that are always, and I mean always, slowly moving. So when two of these huge continental plates collide, the compressive stress is just enormous, way more than enough to buckle and fold solid rock on a continental scale. So here's how it all goes down. But remember, this is playing out over millions and millions of years. First, you get all these nice, flat layers of sediment stacked on top of each other. Then, the tectonic plates start pushing in from the sides. Deep down, where the rock is hot and ductile, it starts to buckle under that pressure, eventually forming that classic, beautiful, wave-like pattern of anticlines and synclines that ultimately build up into a mountain range. So let's just circle back to the main point, because this is what solves the mystery. It's that very specific combination of things. You need the immense compressive stress from plate tectonics, plus the super high heat and pressure you only find deep inside the crust. That's what allows the material we think of as totally rigid to deform in a ductile way, to flow instead of fracture. Now, these folds, they're not just some pretty geological feature to look at. As we're about to see, they are actually incredibly important to our modern world. They act as both treasure chests and perfect traps for some of our most valuable resources.
You see, the very shape of a fold creates the perfect geological structure for trapping things that are trying to move around underground. They can trap groundwater, creating massive underground reservoirs called aquifers. They can concentrate fluids that carry minerals, creating rich ore deposits. But the thing they're most famous for trapping is hydrocarbons. And that right there brings us to their biggest economic impact. For more than a century now, geologists have been on the hunt for these very specific folded structures, these anticlines, because they know they're the single best place on the planet to find oil and natural gas.
This whole idea is known as the anticlinal theory, and it's actually a pretty simple concept. The upward arch of an anticline basically acts like a dome-shaped lid. If that dome is sealed by a layer of rock that nothing can pass through, well then anything that's less dense than water, like oil and gas, is going to migrate upward and get stuck right at the very top, at the crest. And here's exactly how that works. Oil and gas are way lighter than water, so they're always trying to float up through any porous rock layers. But when they hit that impermeable caprock of the anticline, well, they can't go any further. They're trapped. And then they separate out perfectly by density. You get gas at the very top, oil in the middle, and water filling in everything below. It's a perfect natural reservoir, just waiting to be found.
So, if there's one thing to take away from all this, it's that these incredible bends in the Earth's crust are so much more than just pretty scenery. They are the result of truly unimaginable forces acting over mind-boggling timescales. They are the silent architects that have shaped the mountains we see and stored the energy resources that literally power our civilization. Which, it kind of leaves you with one final thought. If something we think of as being as solid as rock can be bent and folded by forces we can't even see, what other powerful silent processes are shaping the very ground beneath our feet, right here, right now?